I don't think I'm sharing yet, so let me share that. So hopefully you can see my slides, and you can see that I'm switching. Yes.
Yeah, looks good.
Looks good. Okay. Okay. Welcome everyone. This is our 58 meetup, almost 5 years into the meetup since 2019. And we have a very interesting topic today. It's the part 2. It's actually chapter 2 of the Modern C++ design book for Andrei. I'll get some of the history and context in a second, but that's basically a kind of a laundry list of what we're going to cover in this hour. I think the last one, just put my pointer. The last one would be probably towards the end of the hour, and I'll just the last 4 or 5 slides are pretty busy, and I'll just put it there. You can take a look at the TypeTraits just offline. Once you get the idea, it's pretty interesting to see how the building blocks are being handled all the way to something more and more complex. But the basic is pretty simple. You just build complicated stuff, which are necessarily like complex and more sophisticated stuff on top of that. Okay, so if there are new members, welcome. Super happy to have you in the meetup. What we do here is we meet every month for about an hour and just chat about C++. I do have a guest next month for Feb. He's from Europe, so it would be a different time. So look for my announcements soon. I'm finalizing with him the agenda, and it's going to be interesting. And I'm looking forward for the next session to attend his talk. If you would like to present anything, please let me know. I'd be more than happy to accommodate. And if you'd like help, ideas, and all of that, I'm here to help. This is sponsored by Qualcomm Wireless R&D Software. I'm a Qualcomm employee, but this is completely outside of Qualcomm. Qualcomm helps to pay just as a generous part from Qualcomm paying for the meetup fees. Every 6 months, I have about $100 that I need to pay, and Qualcomm is paying that from a generous part. Wireless R&D is the department that is paying for that. This might change in the future, but right now this is the all the way to Feb. I think this is paid already paid by Qualcomm. And by all means, just a disclaimer: this is all my own opinions, and all. I'm just a Qualcomm employee, but it's nothing related to Qualcomm here. It's all C++. Dropbox link is here if you wanna take a look at the slides. Discord, ask me for a link. It keeps changing the invite. I have mostly announcements, but some people use that also for discussions. There are by the way, there are other discussions, good discussions on Discord, on C++, multiple of them. If you happen to have to be a Patreon of one of the C++ trainer, you have access to their Discord also, and it's pretty fun to see the discussions there. The SDCPP Meetup YouTube channel is where I upload the all the recording. Recent sessions are uploaded. I do my best to upload as soon as possible and kill my family bandwidth while I'm doing that. I have a Twitter account where I have announcement and seminar, and also my own Twitter account is here. Again, my name is Kobe. I go by Kobe. My official name is Jacob. I lead the Cloud AI 100 software. It's user-space software for the AI card that Qualcomm is producing. I was also the technical reviewer of a book with Dorothy Kirk. That the book is there, and I had a couple of appearances in CPP cast that you can also take a look online. Okay, so I'm going to just mute everyone because I hear some, but just feel free to unmute yourself. I just hear some small background noise. So and I muted myself accidentally, but now I'm fine. Okay, going back to the slides. Okay, so modern C++ design, I already discussed that in previous session, so I'm not going to delve on that a lot. This is the chapter, the second chapter. I already mentioned last time that the first two chapters are pretty amazing in the terms of if you happen to be to be a new programmer in C++ domain, these two chapters provide you access to a wonderful world of meta programming, and the first two chapters are the basic building blocks of this whole domain. So I recommend you either read the chapters or take a look at either my sessions or other sessions that are having similar content related to Andrei's book. This is a 20 plus something years old, still a great book, by the way. So obviously it has some syntax which is can be modernized, but the ideas are very, very relevant for today's as well. Okay, so let's start with compile time assertions. So the idea behind compile time assertions, as opposed to runtime assertions, is to have something which is static and compile time checking. So let's say we want to develop something which is a function for safe casting. Safe casting, which means I want to cast from one type to another type. I don't want to narrow or lose information. Uh, so if I have a large uh, uh, type, I don't want to cast it to a smaller one. I want to have a compile time assertion. Remember that C++ is a strongly typed system, and we have information in compile time that we can infer from. So let's start with uh, baby steps. So here's a function. It's a template function that has a to and from as the template parameter, and we have an assert. This obviously not a, if notice this is not a compile time assertion. This is a runtime assertion. So we have a size of is a compile time construct, but the assert itself, there is an if and abort and all that happens in runtime. The idea here is that size of 2 is greater or equal to the size of from. Okay, so we don't lose information. And then if all good, we can reinterpret cast and all is good. And the way to invoke it is this way. Basically, the way it's being done is that from is being inferred from the parameter that we pass, but the 2, which is the return value, is basically passed as a template parameter. So that's basically how we are going to invoke that. So this would work, but this, as I mentioned, happening in runtime, can we do better? Can we do it in compile time? So this is where everything starts to be more interesting. So let's say that your system has pointers that have specific characteristics, and let's say that we can differentiate between arrays that they have a specific size versus another size. We'll take a look at that later. But for now, we assume that your compiler would complain that you have that we create an array of length 0. Okay, so let's see what happens here. So we have this static array, static check macro, and it has this expression. Okay, so the expression will be either true or false, so either 1 or 0. So this is already a better step than having an assert, which is basically a runtime. This is a macro that creates something. This something is array, and this array would be either one size of a character or 0. And if you have 0, you'll get an error saying I cannot create an array of size 0. It's better. First of all, it's compile time, but it's not great. It doesn't say much. It doesn't say, okay, this type character is too narrow. It doesn't hold the pointer and so on and so forth. So this is how you're going to invoke that. So the next part would be, can we build on top of that, but have something which provides some information in the compile time error. By the way, if you have any questions, you don't need to wait for it. You either wait for the end, or you just make a note and wait to the end, or just stop me anytime and I'll try to address that. Okay, so this is where things getting more and more interesting. If I need to point on few slides, this is one of them, that if you understand the slide, you understand TypeTraits, at least the smaller atomic building blocks of TypeTraits and the whole craziness of templates and template meta programming or generic programming. This would be the slides that we have here. Okay, so a better solution is, okay, let's rely on a template, and we have information in the name. If we are lucky enough, compiler would mention the name of the template in the error message. Okay, so what do we have here? We have another macro with expression, and we have this compile time error with expression not equal to 0, and instantiate this struct. This struct is a compile time error. Okay, so let's take a look at the struct, because this is, I think, one of the, at least when I was reading the book 20 plus years ago, when it was published. And again, I read the book like immediately when it was published. It was mind blowing. So you can see that we have a template here. That's a NullType template parameter, which is not important right now. Compile time error. We're not even defining this the main template. We don't. And then we have explicit specialization of this with true. Okay, so what really happens? So this compile time error is instantiated here. It's going to be instantiated either with true or with false. If it's true, we're good. Why? Because we have definition of compile time error. We create an instance, compiler is happy. But if we have false, and I'm trying to do something with it, which is basically instantiating, the compiler would complain. It would say that there is a compile time error, false, and it's undefined specialization of this specific construct. It's a bit it's a bit better message. It gives us the better part is that it gives us some more information that this is not some arbitrary compiler, but basically there is something intentional from the author of the code. It's already a better one. Let's try to elevate it a bit more, just building on top of that. So here's another. Someone wants to ask something?
Yes, sorry.
Yes.
Question on the prior slide.
Yes.
I don't understand how the parens that you're pointing at do anything. I mean,
it's instantiating. It's instantiating. Think about this. So forget about it. It's a template. Think about it's a struct foo. Okay, and I'm creating an instance of foo.
So shouldn't that be curly braces then? The
Oh,
modern C++?
so yes, so
That confuses me.
no worries, that's fine. So let me you just reminded me something. So in some slides, I was lazy. This is one of the slides that I was lazy, and I did not modernize the code. Okay, this one doesn't have issues in terms of the most vexing powers or something like that. But there are many slides that, and I'll point out that I actually did. I was less lazy and I modernized the code. For example, I changed type def to using so if you look at the book, unfortunately, if you remember before C++ 11, we couldn't have the closing angle brackets without a space, right? It was like it was like considered like a chevron operator. So all of that stuff I changed, but I'm sorry, I apologize that some of them would not be modernized. But you are right that curly braces would be more modernized today. Hopefully it answers your question. It's just instantiation. Does it answer your question? Yeah. Okay, there is someone else that has question. Yes? No? Okay, I'll continue. Just stop me if you have any question. Okay, so let's have some more information that we can put into the error message. So again, I have this macro, and I have the expression. So we still build on top of the expression, either it's 0 or 1, so we can have this differentiate, like instantiation of the templates, but we also have a message. And the idea here is that this message would be concatenate to some class. There is no definition of the class. It's like just forward definition. That's it. Nothing special. And we just going to pass an instantiation of that to something. I'll explain in a second. So again, we have the compile. This is an example from Loki. This is exactly what the book has, and I explained about Loki previously, about the library. So the interesting part that you have is this part. Okay, let's try to unwrap what we have here. We have the main template struct named compile time checker, and it has a constructor. The constructor has ellipsis, can get anything. We're not doing anything. We're not running anything. It's just all compile time games. But we accept anything. And this anything is important. I'll explain why. And then we have false. False doesn't have a constructor that takes all kinds of arbitrary types. So this is the explicit instantiation that we have. So we have two of them. So everything that is evaluated true here in this expression, compile time checker would be chosen here. Everything else would be false. So let's see what happens if we are on the true path. So there is a true expression, which means the expression is not 0. So we actually taking this error with the message, like we're creating basically a name of some class. We're not defining like the class. We're not doing anything. We're just passing an instantiation of this to the compile time checker. We don't care about anything because we're not actually running anything. We just want something that accepts everything. And this ellipsis is one option that can be used at least before 11. Today we have probably better ways to do that, but this is still works well. So if you have true, you have this constructor that takes anything, and compiler is happy. If you have false, you don't have that. You don't have a constructor that takes error underscore. This is not going to work kind of a class name. Okay, so this is basically how the whole mechanism is going to work, and it's all just games during compile time. And if you understand all the way to here, you basically understand the very basic stuff of how we can dispatch. In compile time, we dispatch all kinds of expressions to various constructs. The funny part is I once attended a almost a week worth of session with and Andrei was one of the trainers, 3 trainers, Herb Sutter, Andrei, and Scott Myers. And I remember something that still, it was like 2007 or 8. And I still remember something that he said, that Andrei said about all these games is you create something, but it does nothing, right? You just create something that the compiler would match it to some specific construct, but nothing is actually running in runtime. It's all compile time games, and it's still stuck in my head about like how things are being done in compile time. This is really helpful. So this is how you're going to use it. So this static check macro now has 2 arguments that I'm going to pass. One is the expression itself. So it's this one, right? That is evaluated. The second one is a message that I would like to be appended to this class, error underscore something. And this, obviously, this needs to be a valid set of characters to be a class name. So just remember that. But it's easy here. A valid one, destination underscore type underscore to underscore error. This will be appended to the error, and I'll get this error underscore with the message if I'm failing the expression, if my safe pass is failing. What does it mean? So to make life easier for you, this is how things would look like if I need to expand this macro, and this is how it's going to look like. This class error underscore something is created, just nothing basically happening here, and then we pass that instantiation to this either the main template or the specialization. The main template has ellipsis on the constructor, it will accept it, all good. Otherwise, the false path would say there is no such thing, and the error would include destination type to error. This is pretty nice because then I have this information as part of the error. So the macro part is less important, in my opinion. The more important part is for you to understand how we can dispatch using explicit specialization of starting from the main class, which is a template class, to class template, to more and more specialization. We would need this knowledge moving forward in this talk. Okay. Partial template specialization. Let's talk about partial template specialization. The compiler would basically take a look at the main template, which is widget, and then there is a window and controller, and this is specialized, explicitly specialized widget, and there is a specialized implementation, right? So this is fully specialized, but we don't have to go all the way to fully specialized. We can have it partial specialization of widget. This is something that, if you remember from previous talk, this is very kind of valid, and this way I can actually pass any window type, but with a specific controller, right? So this is any window type with a specific controller. The idea is that the compiler would try to find kind of the best match. Kind of, you can think about like a matching algorithm the compiler is doing in order to get things instantiated. And let's assume that we have this problem in our design. Let's see how this knowledge can help us. Let's assume that we have a template, a class template button, and it accepts one template parameter. We can actually have this button passed with any button argument, just like I have here, which is a great mix and match. If you want to take a look at how things would look like and in different different ways. So imagine you have this main template, and this is just a bar type just to show you. So we can have all these combinations, and the compiler would do the matching for us. So all this information is valid, and all this would be useful. Just to remember, the partial template specialization does not apply to functions, member or non-member functions. You can totally specialize member functions of the class template, but not partially specialize member functions. So just remember that. And you cannot partially specialize namespace level, which means non-member class template. Overloading is the closest technique. So what does it mean? It means that if you have a main function template, this is a non-member function, this is illegal because you cannot partially specialize that. But this is fine. This is basically an overloading of the main function. Okay, so so to keep that in mind. This is kind of the restrictions. Let's talk about local classes, which are a great technique in C++ that are not really, I think, not really known and not really used, but it's very, very useful in some scenarios. It's the way for us to define classes right inside functions. Now, in fact, if you don't really know that, you're actually using it implicitly when you use Lambda. When you use Lambda, this is from cppinside.io. When you use Lambda, this is how it looks like. So this definition of this class, this is what Clang is doing. Lambda 218. 2 is the line number. I always figure out that 2 is the line number. I can't remember what is 18, like why they come up with 18. But basically, this is your constant f, and the lambda dot operator is because I'm invoking the operator here. But there is a class inside. So it's useful. It's useful because we can do something very unique that is kind of related to templates, and I'll show it in the next slide. They have some limitations. Local classes cannot define static member variables. There's some sensible rationale behind that. We cannot access non-static local variable, but we can use the template function. Can be used in template functions, and we can also have access to the template function arguments. And I'll show it in a second. So let's assume we have an interface, just like we have here. It's a simple interface. It's a polymorphic runtime interface. And I have a function that creates something that inherits from this interface. What I don't want to do is I don't want to expose the actual derived class to the entire world. I want it to be hidden. And there are many ways to do that, but this is a very cool way because no one can actually touch the class local that inherits from interface. No one can inherit from that class, but I can definitely define this class. I have access to P and T here, which is really, really cool. Actually, I can actually have this adapter function creator inside a template function, and I can new. Obviously, in modern C++, I'll do something better than new and delete, like unique pointer. But that's not the important part. The important part is that I'm creating the derived instantiation, but passing an interface, and no one knows that I'm actually pointing to local, in the sense that no one actually have visibility to local, which is really nice way to hide implementation details. So this is a trick that you can do with template functions. By the way, all these small techniques are being used in the book, so it's kind of a collection of small building blocks that we're going to use later in the book. So some of them are kind of distinct. The next one is not. The next one is one of the also most important building blocks for us to utilize templates in our code to make things better. And the way I see this specific few slides, the upcoming few slides, is a great way for you to turn if-else, a runtime if-else statements into a compile time dispatch. And the reason I'm mentioning this is that in many cases, I'm seeing, throughout my career, I'm seeing if-else statements that the if and the else are actually pointing to some known compile time known constant, not runtime, but compile time known constant, but it's still using an if-else, and we can do basically better. This is one way to actually do that, and let's start with EmptyType. So EmptyType is a very simple way to take an integer and create like a strongly typed construct from this integer. What does it mean, a strongly typed integer? EmptyType 0 is not the same as EmptyType 1. You cannot mix these two. They are not, unless you create conversion functions and similar. You can't really assign an instance that is EmptyType 0 to EmptyType 1. Well, internally, there are integers, which you could basically assign one integer to another. You wrap it with this kind of technique. There are completely two different types. Now, this is one way to do it. There's also this way, but it's the same. It's the same. Like some would use enum, some would use inline. The inline static, the inline C++ feature, static int value equal v. It's basically the same idea. This is a non-type template parameter because it's an int, and it's a great way for us to create dispatching in compile time. Now, a modern C++, I think this is from, if I'm not mistaken, this is from 11. This part is from 17, the bool constant. But this is basically a way for us to create this integral constant that is being used by dispatching to different functions that has different parameters that takes this integral constant. But this is from CPP reference. You can see that I can create these 2 or 4 that they are completely distinct values, right? I can access the underlying value with colon value, but they are distinct values, and not shown here in CPP reference, but there are all kinds of examples that you can see online on using integral constant to dispatch to different functions. Scott Myers, in his latest book, the one before he retired on modern C++, has at least a chapter on using this technique, which is very, very interesting, by the way, if you have a chance to read about it. So let's take a look how we can use this, what we call tag dispatch. You want to use it when you want to call several different functions, but it depends on compile time constant. Remember, I told you that one of the use cases is I have an if else, but I can do better in terms of how I dispatch that in compile time. So you can do it in compile time, and let's see how this is possible. So let's take a look at a specific class. We name it Nifty Container. It's a very simple class. It has it's a class template, has a T, and there is a Boolean. It's a NullType template parameter, is polymorphic. Okay, so there is a function, member function, do something, and we create this if. If it's polymorphic, we do something. Otherwise, we do something else. Now, this looks nice, but it's not going to work. The reason for that is if the type T, if it doesn't have this clone, this would fail to compile. Like this whole thing. Why? Because the compiler would need to verify this whole thing, even if it's kind of confusing. It's a template parameter, but it's not. But it's part of the whole function. It's not going to be a two different separate compile path. The whole unit would be verified, and the compiler would say, "Hey, can I have?" Let's say it's an integer. So it would say, "Okay, does integer has clone?" It doesn't, and then it would error out. So we gain nothing. So it's not really working. Okay, so let's see how this is. How can we do better? Tagging for the rescue. So instead of having this one function with the if else, I split it into two functions. I have an int to type true and int to type false. The whole idea of int to type, it's a very lightweight vehicle to pass as a parameter. I pass an argument that's very, very lightweight, probably gonna be compiled out. I don't even have a parameter name. And the idea is that this is a private section. I have the main do something, the one that used to be here, dispatching it into two different functions. If you remember from my previous talk about what is being instantiated, if into type is polymorphic is true, this would never be instantiated, and vice versa. So if if the compiler pick this path, the fact that, let's say, an integer doesn't have a clone, no one cares because this function would never be instantiated. Just take a look at this slide, because this is one, like, try to imagine how you can fit that into various applications in your code, because this is a very useful, and as I mentioned, try to get Scott Meyer's latest and recent book. That, say recent, I'm talking about a few years back, maybe 10 years. He has at least one chapter on tag dispatch. It's super interesting, very advanced, but super interesting. This is the building block of that part, which is really cool. Okay, so we have into type, but we can also have type to type. So let's take a look. What does it mean? So here's a function that we call it create. Sorry. And let's say there are so this is basically just a template function that creates something. So this function, obviously in modern C++, I would not use new and delete. I'll use unique pointer. that's the less important part here. But just imagine that there is a single argument constructor in the system of T, and the argument is U type. But let's say that the system, I have a legacy system, and the objects of widget, I can't touch it. It's a legacy widget. I can't touch it. Unfortunately, it's not going to fit to this create factory. It doesn't fit into that. Why? Because widget needs to have a second parameter to the constructor, and the second parameter is -1. Okay. So Yeah, I could create, I could write this create widget function. I can create another function, create widget just for the widget, but it means that I don't have a uniform interface. So people that needs to create widget would use my create widget function. Everything else in the system would have create. Not beautiful, probably the most common solution that people would pick, but there are actually better ways to do it. Okay, so first of all, I cannot do this. This is illegal. Don't try it. It's not going to compile. I can overload. This is not going to work. I can overload. I can pass a dummy uh, parameter, like a dummy argument to this dummy parameter. So if I have widget, this is overloading, right? So if I have widget, I'm creating a widget, passing it, and then I'm creating this special case widget with a -1 as second argument. It's not beautiful. There's a couple ways, the couple reasons why it's not beautiful. One is it's ugly. You can see that. The second is I need to create this arbitrary object. Might be complex. Yeah, it might be optimized, but it's still ugly. What do I need? I just need something very similar to what we saw before, just a light vehicle transporting the type information about what is the T. Okay, so type to type is to the rescue. Again, type to type of int is not the same as type to type of widget, is not the same as type to type float, and so on and so forth. There are there are completely distinct types that I'm creating. Basically, I'm creating a strongly type that is derived from other type just to make this differentiation. Okay, so let's see what we can do with that. So now I have this main function, template function definition, T with some U, and type to type T is everything that fits into that, whatever matching that compiler has, compiler would pick that. But I have a different overload. Again, it's a U, it returns a widget, it takes the U argument just like the other one, but I have type to type widget. So what happens is that when I create type to type widget, and the compiler, not I, but the compiler is overloading, this would be a better match. And this would be picked. And everything else in the system would use that one. It's a super powerful. I don't need to create anything heavy. This would be probably optimized out as well, but I'm not creating anything heavy. It's just a vehicle to do the type dispatching that I'm describing. So type dispatching is a great tool in your toolbox when you start thinking about different path in your code that has enough compile time information. And this is something that I always ask myself when I write code or review code about, do I have enough information in compile time that I can do something else? Which leads me to the next section, which is type selection. So type selection is, a long story short, given a specific expression, I can have a specific type versus another type. Okay, so try to imagine this struct that has this two template parameter. One is T, one is polymorphic, and the value type. This is where, by the way, this is where I modernize the thing. It's using and not type def. Was lazy in other slides. Value type is T pointer. So this is basically where the type def kicks in. And I have this partial specialization where I have false and then value type is T. Okay. And I have this, just this basically you can look at it as traits. It's not anything else but traits. So I have this main struct and specialization. I have just one. This is enough. And then this nifty container is going to use the traits. You can see that this is how we use that. So the idea behind traits is that we have this main struct or class definition template one, and then all kinds of different specialization. We'll take a look at more and more examples. It will be clearer. And then you have another template related code that is using these traits, and the traits, the value type is the interface of the trait. Why? Because I'm using : value type, and I don't really care what is the value type itself, as long as whoever instantiated my trait instantiated with the correct traits. So if you think about stud string, for example, if you look at stud string, it's basically a type def of stud basic string, and it has a trait, a character trait that has all kinds of this, I call it interface, the kind of the trait interface. It's basically all kinds of enums and similar that the string, the basic string, is using to understand what is the character type and other related features. And by doing that, I can instantiate my basic string with different characters. Like I can pass wide characters. I can have all kinds of stuff, but the basic string class stays the same in terms of how it's actually creating the members and dealing with that. So so that's one way to create this type traits. It's a bit clumsy. We'll see how we can do it a bit better. Okay, so this is one way to do that. This is another way. Anyway, sorry for this typo of this using. So let's assume we have a structure named select. And this select has 3 template parameters. One is a flag. It's a non-type template parameter. And then we have T and U. Okay, and the result, what is the actual type that I would like to have, would be, by default, would be T. Now I'm doing this game of specialization. The first, so take a look, the first template parameter, I set it as false. So if I instantiate select with false and then T and U, some T and U, the instantiation that would take place is this one, and result would point to U. Anything else which is true, flag is true, would be result equal T. So back then, when the book was written, this was basically the analog to what we have today. I think again, C++ 11, stud conditional, and we have stud conditional T, which basically it's a syntactic sugar to expose the type. It's the same idea behind select, and used a lot. By the way, I used it a few times when I had a compile time expression. Sometimes I would take from the compiler switches the -d, if you talk about Linux or Unix variants, a dash capital D. I have some expression like something that I can put here as the Boolean, then decide if it's a T or an F, and I can have a whole different 2 different types. They're not related. They're not inheriting from base type. They just have the same interface, which is basically duck typing. So that's basically a very interesting way to create that. Then this is the very easy, straightforward, but you can have more complex stuff. This is just int and double, but just imagine that you have actually different class types that you implement for. Just imagine that you have 2 different architectures that you build your code, and you pass the architecture or something that denote an architecture in your people processor -d in your compile line. Then you can take that, put it here, and then decide if it's one type or the other type. It's just nicer than having like an if-def, a preprocessor if-def that you can also do that. But this is actually nicer. This is just one example of how you do that. So this is how we're going to do it with the select. Stud conditional would be exactly the same, just not colon result, but type. And we just type def it. And if it's polymorphic, we'll do t pointer. Otherwise, we'll have t. Everything else behave the same. I have about 8 minutes to finalize a few things that I would like to do. And this is related to detecting types that are convertible. One is inherited from the other one. This is a great example of how we can utilize this whole compile time games. We basically want to have given two, getting information given two arbitrary types. Can I convert one to another? So if I have a base class and a derived class type, I can pass the derived class to the base class. Okay, the whole solution is based on size of a specific type. And here's how we start building that, and hopefully within 10 minutes we'll probably end this section, and I'll take questions. So two expressions. One is a type def of a character. So character, let's say it's a 1 byte. I don't know how much, like I don't know in terms of padding and all how much is big, but big is more than small. Because it has two characters. So I know that I have two distinct types. One is probably 1 byte, and one is at least 2. Okay, so that's one building blocks that we have. Okay, so we have a function named test. It returns, one returns small, one returns big. The one that returns small accept you. We don't care about the parameter name. We don't actually do anything. It's all about remember what Andrei was telling when I was attending his session. We're returning stuff, but we don't doing anything. We're just returning stuff. So the compiler would do something with the type for another maybe chain of expressions to obtain information eventually. So if I have a U or something that is convertible to U, test would be taken. Otherwise, anything else, this is why I have this ellipsis. Anything else is going to be passed to test. From that point, it's pretty easy. A conversion exists if I take a specific t, whatever t is, I instantiate it, nothing is really happening, it's all compile time, and pass it to test. If t and u are convertible, like if I can pass t and u can accept it, small would be returned. Again, nothing is in runtime, it's all compile time. And then the size of small would be size of small. There is one wrinkle here. T as a type needs to have it. I'm actually making here an assumption that T has an empty default copy default constructor. So just like anything in software architecture, you can solve it with another level of indirection, and this level of indirection is make T. Make T is funny because from creating T, I'm creating a function that just return T. I call this function. Now it's good. T is not created. We don't care, but there is a return value, return type. The type is T. Is T can be passed to test with U. If yes, size of small equal size of small. Now in modern C++, you don't need this make T. There is something which I don't think it's really common in terms of like knowledge, but there is decal val that I can actually, this is really actually very cool. If you have, this is mostly for generic But if you're writing generic code, you probably dealt with declval. So declval basically allows me to take a type that has non-default constructor, what we call the empty default constructor, because it's deleted here. But I can still create an instance of it because I want to do that through and do decl type. So if you know about decl type, again, it's all compiled down. There's nothing running. Nothing here is running. I created an instance of non-default, created an instance. That's foo because I wanted to do the decl type of whatever is returning from foo, which is an int. So this whole line is basically int. So this make t in modern C++ is declval. So again, if you're writing generic code, this is something that you're gonna need. Then you can package everything in a class and have this enum exist, and all is packaged really nice, and you can use it with exist. So is double converted to int, it would be 1. The second one would be 0, and the third one would be also 0. By the way, the third one is pretty interesting. Stud vector, if you look at stud vector, it does implement a constructor that takes stud size underscore t. But this is going to fail in terms of it's going to return 0 because the constructor is explicit. So this is interesting. This is interesting take that even though there is a conversion between stud vector, it has a constructor that takes size t. The constructor is explicit, so the implicit conversion doesn't happen. So this is pretty interesting part. If you want a conversion of, do I have the same type? Take a look at how, so I can have all the baggage that I had as before, and I can add another enum that by default t and u are not the same type. Then I have a partial specialization. What happens if someone instantiate t with t? So this is where the compiler would match this partial specialization because t and t are the same. Exist would be 1, same type. It's because there is a conversion between these two. From that point, I can build. So these are all the building blocks of start building all kinds of smart type traits. By the way, fortunately, lots of type traits are implemented for you in the standard library, but if you want to have your own versions of your own specific type traits that are not implemented, you are more than welcome to do that in your code using this information. So, and then you can actually start building all kinds of macros. Is something is a superclass of something, so there is a conversion between pointer and pointer. I'm putting const, not me, but Andrei putting const, so we're not failing because of the const. If you don't want to have a conversion, you don't want to have a conversion to void pointer. If you don't want to have a conversion with yourself, you can add this. So it's a superclass strict. You can have so I am a superclass, you from T, but I'm not the same one. I'm not the same type. So if I want to have a more strict definition of that. So we're running out of time. I just want, as I mentioned in the beginning, the last 4 or 5 slides, I'm not going to go in details. The book, the last part of the book talks about TypeInfo wrapper, which since we have lack of time and I knew I'm not gonna manage to get it. It just provides a better, more useful type info. That there is a problem with the type info, the type underscore info that the standard provides because it's disabling the copy constructor and assignment operator. We cannot store objects of type info. You cannot. There's a lot of restrictions. So what Andrei is doing in this part of the chapter is creating a type info wrapper that is capable of doing all the things that the regular type info that provided by the language is incapable of. And from that point, you basically have everything you need in order to start playing with that. Just to finalize this part again, I'm sorry, I don't have a lot of time. I just want to mention that he defined a couple of types. One is null type, and one is empty type. Empty type and null type are not the same. Empty type is I don't care, and null type it's a marker, and he's using it heavily in the third chapter where he has lists, and you want to denote the end of the list. So null type would be, it's like if you know Lisp, it's basically nil at the end. The one thing before we kind of finishing, give me another couple minutes. TypeTraits are super important, especially in the standard library, and you can take a look at the last six slides. TypeTraits allows me to optimize specific code path, and copy is one example because there are multiple ways to define implement copy. This is a template function. I can I can have copy one by one, and this is fine, but it's not optimized. What if I have data that I can actually mem copy, right? So can I infer information from the type that I have in compile time to say, okay, this is actually a type that has a characteristics that I can pass to a copy function, that maybe the default one would do a copy one by one, but a specific overloaded plus specialization would do a mem copy, or maybe it's even do something even more fancy than just mem copy. So this is where type traits are kicking in very heavily, and in a nutshell, you can see that there are you can build a type trait class that has a lot of information about is it a pointer type. So take a look at how we have a nested struct inside the type trait. That this is just a main struct that has an enum that says no, I'm not a pointer. But if I'm instantiating it with you, that is a pointer. So this is where the instantiation kicks in, this part. This will be a match in case of a U. Then the pointer type is U and not null type, and the result is true. And then on top of that, I can build a lot of things. I can have so there is a part of the book which says what is the best way to pass parameter to a function. You can actually make this kind of things very smart. Like parameter type can be just regular non-pointer, just pass value if it's simple, and so on and so forth. Versus the other part where it's more complex. So let's pass a pointer type. So this is something that you could use also in specific code path that you need. So I knew I'm not gonna be able to cover everything. This is just an example of pointer to members. This is a very interesting specialization where you have pointer to member traits with you, and this is a pretty interesting, that's really hard to see in the wild, but it exists, specialization where you have a pointer to a member, which is this is the way it's actually being. This is basically the class. This is the type, and this is just the syntax. It's very weird syntax, but it is basically how it works. The TypeTraits itself has lots of examples in towards the end of the chapter. I'm gonna skip towards the end. This is just stripping const and just going back to the summary because we kind of running out of time, and I knew the last few would not be into the session. So compile time assertions, partial template specialization, tag dispatching, either into type, which is kind of integral constants. We have selection. We have tag dispatching also with type to type. We have selection, which is stud conditional. How we can convert. We talked about decalval, TypeInfo wrapper over type_info, which gives us value semantic. And then we talked about all kinds of markers like NullType and EmptyType placeholders. The last 4 or 5 slides is basically providing you an example of a complete type trait class that was taken from the book, and probably these days, the opportunities to have type traits classes are even you can have more and more opportunities to do more of this interesting ideas. So most of the type traits are, a lot of type traits are defined in the standard library, but you can also create your own. I basically I have a lot of type traits in my applications, code that I'm writing or code in my team that we need in order to dispatch and get information just by instantiating a template with this type trait, and all the characteristics of this type trait are within this specific specialization, and from that point we can achieve a single uniform interface, which is very, very interesting. It's like, take a look at that again. If it looks confusing, it is very important in order to understand more complicated code of template from C++. Questions? No questions. Okay. Okay, so I'll close the session. Thank you everyone for attending. Remember, next time we have a special guest for Feb. It's towards the end of Feb, by the way. Just mark your calendar. I'll announce it both on the Meetup page, on Discord. Let me know through Meetup if you need the Discord invite. Thank you. Have a good rest of your day.
Thank you.